Okay, good morning. Hi. Thank you very much for coming back. I got two feedbacks yesterday. One was nobody down the back could hear me, so hopefully the sound quality is better now. It's just been checked out. So, but wave if I disappear again. And the second one, the films from the tunnel. Somebody said I should do it on a bike, so it was faster. Okay. So the third one of the visit to the tunnel, I've actually gone into fast mo, so it goes a bit quicker. But the first two are me just walking along, I'm afraid. So today, start with the RF. Okay, this is the RF is this is a huge area, and it's populated by dark wizards who sit in Faraday cages and are very smart. So, but I'll just give you a brief introduction of what this is in the LHC. So the idea here is we want to excite an oscillating electric field in the direction of the motion of the beam. So the beam's coming through the cavity, and it will see an oscillating electric field. Well, it won't see an oscillating. There's an oscillating electric field in the LHC at 400 megahertz, and we're going to time the passage of the beam to go through the cavity when the field is pointing in the right direction, or even zero. So that's the basic principle. So here you have the electromagnetic field, the mode that's been set up in this cavity, the surface charge, and the surface currents that flow on the surface of the cavity. And the two main purposes of the radio frequency system is to bunch the beams via longitudinal focusing and accelerate the beams during the ramping stage. And the LHC RF system is down in 0.4. So this is these are cryo modules. There's 4 cavities per module, 2 modules per beam. As I said, 400 megahertz. Flat out, they're going to deliver 16 megavolts of accelerating voltage at 70 eV. This is niobium sputtered onto copper. And these are cooled at 4.5 K and quite a large beam pipe diameter, so low impedance presented to the beam. And if we go down into 0.4, we actually open up the distance between the beam pipes with the D3 and D4 magnets here, dipole magnets, so we can fit the cavities in on beam 1, beam 2. So completely independent systems for beam 1 and beam 2. And that's what it looks like from the control room on a bad day. So each one of these, this is a line, is a cavity. So independent control of the power and the RF low level. And here you can see the power in and the volts that are being delivered by the individual cavities. So when we're operating with beam, all that is green. If we trip a cavity in physics now, the beam's dumped. Okay, so there's a lot of attention goes on. This is more of a joke than anything too serious, but this is their vision of one. This is from Andy Butterworth, from the klystron through the circulator down the waveguide to the cavity. So this is actually generating the RF power that's being fed into the cavity, and just the kind of controls behind that to actually keep the phase, the power, the voltage where it should be. And there's even feed in from the beam here for the first turn, one-turn feedback. And also on the low level, again, almost incomprehensible, but beam 2, beam 1 going through the cavities, there's pickups on the beam which are feeding into the system. And essentially what we'll worry about are the phase loops, keeping the phase stable, the radial loop, radial position in the ring, and the synchro loop. Okay, so that's it's a complex system, and we see that as a rather black box in operations, to be quite honest. Just some more than others. So I just want to briefly go through synchron oscillations, just so you know it's what they're, the bunching mechanism that's provided by the RF. So we imagine a synchronous particle with the right momentum coming round into our cavity at time 0, at the right phase with the right energy. And so here we have volts, and here we have delta t with respect to this particle. So this is T0. Okay, that's sitting on the so if it comes up here, it's going to see a positive voltage. Comes down here, it's going to see a negative voltage. And so we remember from yesterday that our lower energy particles are going to get bent more by the dipole fields as they go around the ring, and they're going to have a shorter revolution time. Higher energy particles are bent less. They're going to go further as they go around, so they're going to have a longer revolution time. And if we go into delta E versus delta T space, so this is the delta between the synchronous particle and another particle, hypothetical particle, and the time difference between the arrival time of the synchronous particle and this hypothetical particle. Okay, here we can see what we will understand to be the RF bucket and the bunch. So this particle here has the same energy as the synchronous particle, but is arriving before the synchronous particle. We won't ask how it got there, but let's just say it's there. Okay, now this sequence, thanks to Rende-Stierenberg. So this particle, because it's further up the slope, it will pick up more volts and more energy than the synchronous particle. So it will catch up with the synchronous particle, but at the expense of gaining energy. And so it catches up with the synchronous particle, so it's going round at the same time now, but it's got too much energy. So off it goes down the slope, picks up less energy, keeps going, and okay, now it's got the same energy, but it's in front of the, it's arriving in front of the synchronous particle, and around it goes, and performs what we call a synchrone oscillation. So this is phase focusing. So these particles are kind of kept bunched by this mechanism. So it's a very, very important feature of longitudinal motion in the LHC. Synchrone oscillations are very slow. These particles, in fact, you imagine you've got these 30 centimeter long particles. The particles are moving backward from one end of the bunch to the other. Very slow. This is sort of 40, 50 hertz in the LHC. And okay, so when we're at steady state, the particles as they go around aren't losing too much energy. So in fact, there's not. So our synchronous phase is actually practically is pi. So we are sitting here. So it doesn't need the actual beam, the ensemble doesn't need to pick up energy from the RF system. So the particles with energy deviations from the synchronous particle are oscillating around here, but as a whole, the synchronous phase is 180 degrees, and we move up here when we start to accelerate. Okay, that's the RF. So just a quick look at the beam instrumentation. I won't go into any details here, but this is vitally important. This is our eyes. This is, we're looking at beam position, we're looking at beam loss, we're measuring the tune, we're measuring the emittance, we're looking at the structure, the bunch structure around the ring. We're taking synchrone light from the beam to try and measure the transverse beam size, etc. So this is a critical system for us. I'll just pick out the two really important ones. The big extended system. So the LHC BPM system. Okay, there's 1,088 button couple of monitors out there giving us X and Y around the ring. So these are distributed around the ring, and for both beams, they're feeding up the horizontal and vertical position of the beam at these points. And this allows us to produce pictures of the closed orbits of beam 1. So horizontal beam 1, vertical beam 1, horizontal beam 2, vertical beam 2. And here you can see what we discussed yesterday, the separation and crossing angle bumps of in the 4 interaction points. Okay, that's one thing that's sitting right in front of us all the time in the LHC. And you can get the scale of here. So we've got 27 kilometers, and we're keeping the beam down the middle of the pipe to within plus or minus 7 millimeters. The other really important system is the beam loss monitor system. Okay, this is a beam loss monitor at 0.2. So they've been drawing on the magnet, but not on the beam loss monitor, which is very nice. So there's around 4,000 of these protecting the LHC against quenches or damage from beam loss. And these are plugged in to the machine protection system, so very reliable, so safety integrity level 3. They're integrating over 40 microseconds, so half an LHC turn, and they have thresholds, and they will dump if a single monitor goes above threshold. So these are active all the time, and if any one of them goes above threshold on any time scale, the beam gets dumped. And the thresholds, most of them are stuck on superconducting magnets, and with a dump threshold set to some fraction of the estimated quench level. So the idea is these guys will not only protect against damage, they protect against quenches. So if we dump beam in, of course, we're going to put heat into the magnets, potentially quench the magnet, and the idea is these guys will actually dump the beam before we get to that stage. And we've done a very good job.
Right. What's the mean time between failure of those? What happens if one of them fails? If you have 4,000 of them?
A BLM fail? In fact, these are very reliable. The front end, the hardware at the front end. What we do have occasional failures is with the electronic chains that come up, and I'd say maybe 2 a week, something like that, where we have to actually stop operations and either give access or somebody has to go to a surface building to change a card or something like that.
So if one fails of this electronic change, then you dump the beam.
Yeah, if they think that the functionality is compromised, this is all pre-decided, then we will dump the beam. The operator will do a first level diagnostics, then it's on the phone to usually Christos to go and fix the problem. So this is what we see in the control room. So this is from Fabio. So this is the beam loss display. Again, this is right in front of us all the time. And here you see the losses normalized into grays per second, a log scale, 27 kilometers, and the red points are the dump thresholds. And you can see they're varying. So we're out in the arcs here, and in the warm sections we can actually sustain higher losses, of course, because we're not protecting against quenches, which is why you see these higher levels here. And this was actually during a beam loss map. As we say, we provoke losses to check the collimator systems, which is why you see the high losses in the collimator section in 7. Okay, some near the beam dump in 6, and some in the collimators in 0.3. But orders of magnitude between the losses in 7 and in the arcs. So the collimators mopping up all the beam and stopping it going into the arcs. Okay, we come to the operational cycle, which is the real sort of bread and butter of our operational existence. Beam dump, we ramp all the magnets down. I'll come back to that in a minute. We inject the beam. This takes about 30 minutes on a good day. The ramp takes about 12 minutes. Go through the squeeze, 15 minutes. We collide, takes about 5 minutes, and then we sit in stable beams, delivering luminosity for between 0 and 30 hours. And we can go from here to here between 2 and 3 hours on a good day. So this is what we define as turnaround. Okay, and we can actually, we can attempt to describe this as a sort of state machine, and drive through these various modes to take us from from, let's say, pre-cycle, pre-injection, injecting probe beam, physics beam, prepare the ramp, flat top. We stop there before we do the squeeze. This is where we collapse the collision at the separation bumps. We go into stable beams, and then we dump the beams. So from any one of these, of course, we can have problems, and the beam will be dumped, and then we have to pick up the pieces and come back around that loop. So that's the operational cycle. Now this is driven from the control room by a sequencer. Roman's there. He's going to have a 3-lecture series on LHC controls in a couple of weeks. So I'm going to go into a bit more detail here. But this is a task-by-task breakdown that everything we need to do as we're driving our way around that loop. As you see, there's a lot of detail here. This is semi-automatic, basically because there's so many things that can go wrong and do. And if you can see here, the prepare ramp, we're hitting the orbit feedback, post-mortem system, safe beam flag, abort gap cleaning, RF checks. We've got Fidel trimming the sex poles, spools, orbit feedback, energy feedback, inject trims into the ramp, transverse damper, BBQ, the tune measurement system, etc., etc. So, you know, a huge list of, you know, we're banging stuff around all over the ring, and that hopefully is a fully consistent, fully complete list of the things we have to do to actually drive us through around that loop. So that's our tool. So that's one of our main tools. I'm just going to nip quickly round what's actually going on as we go through that. Okay, one thing, we saw the Precycle and the ramp down. The aim here, these are the superconducting magnets, and they're kind of very robust, but they also have some interesting magnetic features, and I'll touch on that in a minute. But the aim here is by doing the same thing every time, going up to the same current, coming back down, and then going to the injection level, we get a reproducible magnetic machine. So we stick the beam in, the tunes are the same, the orbit's the same, the chromaticity is the same. And this is something we do fairly rigorously. So this is about 35 minutes. So this is, we come out of access, we pile all 1700 magnetic circuits through the mincer, and then, only then, do we actually start the injection process. Okay, now the injection process, our first challenge is to bring beam from the SPS down the transfer lines. So fast extraction from the SPS down TI8 to 0.8, so injection of beam 2, or down TI2 through Alice for beam 1. Okay, with other clients out there. So in 2012, our maximum was 1,400 bunches, 1.710 to the 11 protons per bunch, 1.8 megajoules. In one batch, imagine you've got this 2.2 meter long train of beam coming down the line, which is almost, which is most of the line, in fact, and then going into the ring. Okay, reasons to be careful. So what the total energy in the beam at top energy is 140 megajoules. Here we're talking about 2. But during an SPS extraction test in 2005, we took 2.5 megajoules into a vacuum, into a magnet downstream of the extraction point in the SPS, during a rather overzealous override of some interlocks, and sliced a meter-long slit down the vacuum pipe. So you can, some red faces. So you can imagine we don't want to do that LHC side. So this injection process has to be dealt with a lot of care. Okay, I'll just go down into TI2. Hopefully this is. Moving the come on down, so the transfer line into TI2. This vacuum pipe in front of us, with the LHC just behind. This is the okay, it's going to get a little cramped as the transfer line approaches the LHC proper. And here we're amongst the dipoles. At the end of the line. And you can see it. Okay, here we're behind two dots. We're going to have a look at that from the other side in a minute. And duck down with these cables and see if we can get all the way along. So this is the transfer line.
Okay, now we're really very close. We have the two warm beam pipes in the LHC and the transfer line vacuum pipe just there. Still a quadrupole corrector magnet, collimator, coming down to the 5 septum magnets.
Okay, somebody's going to have to go back in and reconnect all the cables I pulled out. I think so. Okay, you can see from there the actual beam was coming up from underneath, so it's coming into the septum magnet from below, and okay, here we can see the actual. So the septum magnet are going to bring the beam in horizontally onto the horizontal axis, and the beam actually coming, this shows from above, but coming at the vertical from below, and it's going to be still coming up in the beam pipe of the LHC until it reaches the magnets downstream, which are going to kick it in the right direction, and it'll end up on axis. So the injection kickers here, we're going to go inject some beam, inject some more beam, inject some more beam, inject some more beam. So fast rise time, fast fall time, and a very stable flat top. So they stay up for the length of the 144, 288 bunches that come down the line. So this is an art in itself. I can't really spend too much time on. Just the layout. So we're coming down the transfer line, and this is where we got to in that video. We go through the septa to the kickers, and then we're on axis. And then we rattle on around the ring. This downstream of this is the TDI, which is 2 big vertical jaws about 5 meters long, which are going to come in during the injection process. So if there is a miss kick of the kickers, this will mop up the beam. You can see the challenge. You're bringing these high intensities down into a superconducting environment, and that's quite impressive. And just to okay, this is just to show you from the septa on.
Okay, well, it's the side now. You can see the transfer line, vacuum pipe, and the 2 warm beam pipes going into the 5 septum magnets. So these are going to, so the septa are going to bring the beam in horizontally. Okay, we're at the other side of the septa now. And 2 beam pipes, and the incoming beam 1 is on the inside,
Which is against the wall. Against the wall.
Speed box, and to where the 4 injection kickers are normally situated. And you can see the cables coming in from the outside, and this is where they usually sit, and they're all out for refurbishment during LS1. Okay, carrying on down towards Alice, we have Q4 and speed box. And separation dipole. Okay, this tertiary collimator on the incoming beam, and we come to where the 2 beam pipes join and go into the 1 big beam pipe. Okay, Alice, because it's low luminosity, doesn't need the tan. Okay, here we have the TDI. So this is 2 vertical jaws, which are going to come in during the injection process to mop up things mop up beam if things go wrong. Okay, the TCPD, another absorber protection device, and the superconducting separation dipole.
I think it's amazing we can actually do anything at all, actually. Let me look at that. Okay, just the injection kickers. This is on the other side of the wall, so in the bypass tunnel. Okay, these are transmission line kicker magnets, so it's a special special design. But this is the sort of hardware that's sitting in the bypass tunnel. So these are the pulse forming networks and the resonant charging systems, which are going to drive this pulse into the kicker magnets. Again, very specialized area. So this is what it looks like in the control room and around CERN. Okay, the injection of the beam 1 in blue and beam 2 in red, and that process is going to be controlled by the injection sequencer, which is a semi-automatic thing, which is going to run through these requests and send them to the central beam and cycle manager, okay, which is going to take care of sorting things out in the injectors. And you can see each one of these is a request, and this is the number of bunches, the bunch spacing, the number of PS batches, and very importantly, which bucket number, so whereabouts around the ring we're going to stick this beam. And on a good day, you can run through beam 1, beam 2, either interleaved or fill beam 1 and then beam 2, or vice versa. And this process is checking that all things are working nicely. As you see, we're going to have to worry a lot about losses and beam quality here, transfer line steering, the phasing of the RF, the synchronization, beam quality checks in the SPS. So this is an output from there. They're looking at bunch position, the bunch length, are there satellites, that sort of thing. And they will not extract if the beam is not good enough for the LHC. And similarly in the LHC, there's a lot of checks that that things are good before we continue. So just rattling through this. This is the so we're looking here at the behavior of the extraction, injection kicker, beam loss, the RF, injection oscillations, transfer line, RF phase, and so on and so forth. And this is actually comparing, measurements against references and deciding whether or not it's okay to carry on. And if it's not, unfortunately, we have to go back around the loop and re-steer the lines, dump the beam and re-steer the lines. So this can be a sort of sometimes a painful process. Checking, get the BPM readings from the LHC on the first turn into the LHC and making sure that's within limits. So checking injection oscillations and getting a tick if things are okay. Rather scary plot from Philippe here, but again, when the beam arrives, it's going plopping into the RF system, into an RF bucket. The phase has got to be right. The revolution time, the energy of the incoming beam has to match what the LHC expects. So that is, again, this is something that's up in the control room all the time during injection, and these errors will be corrected if necessary before we start taking serious beam. We're going to measure the beam size. This is wire scanners up to a certain limit. So flying a wire through the beam. So this is in and out, and this will give us the emittance, the normalized emittance, which we learned about yesterday. And this is 1.6 microns. So very, very good. So this is the incoming beam from the SPS. We then, when the machine's full, we prepare the ramp. We load our 1700 power converters, load the collimator functions, load the RF transverse feedback, get the orbit tune feedback on, send a timing event, and then we go and get a cup of coffee. Because once we've started the ramp, which is started with a timing event, there's not a lot we can do except switch the orbit and tune feedback back on if they trip off. And say that we went through that earlier, so a lot of systems involved. And on a good day, that's the result. We've finished the injection process, we've prepped the ramp, we've loaded all these functions, sent the timing event, and you can see we've gone up, in this case, on a good day with very small losses up to the flat top at 4 TeV. So the ramp, it takes about 13 minutes. We start very slowly with a parabolic exponential running into a linear. This is to minimize the effects of snapback here. I'll come to this. And we've got corrections in there for the effects. So I'll go straight to the problem of persistent currents. So this is these superconducting filaments you saw that make up the strands of the Rutherford cable, and they are going to form surface currents to stop the penetration of the B field into the interior of the superconductor, and you get a magnetization from these surface currents. And they are persistent. This is a superconductor, there's no resistance, so these guys can hang around for a long time. And this magnetization really messes with the field quality of the main dipoles. So here we're talking about the 1,232 dipoles around the ring. And they introduce large field areas. In particular, we worry a lot about the sextupole component of this. We saw this drives the chromaticity, and we get huge chromaticity shifts, potential chromaticity shifts, if this is not corrected. Okay, and this is exacerbated because these effects are dynamic. So we have this big error, which will shift the chromaticity by about 80 units if we didn't correct it. And what will happen while we're sitting at 450 GeV is these persistent currents will decay, and the size of this error will get less. And then when we start the ramp, these persistent currents, when we change the B field again, these persistent currents will snap back to their original value. So at the start of the ramp, we get a potentially huge chromaticity shift, which would just wipe the beam out if it wasn't corrected. So that's something which we spent a lot of time, a lot of modelling, a lot of measurements done on the LHC magnets to get that understood and correction mechanisms in place. So that's something we is there all the time, but we appear to have mastered. I don't know about doing this one actually. So we increasing the momentum. So we've learned about RF phase focusing and how are we going to accelerate the beam. So we inject the beam with a 0.533 Tesla at 450 GeV and a momentum of 450 GeV. Okay. So to start the ramp, we're going to increase the B field by a little bit, which is going to, as we know, is going to shrink the bending radius. And our beam will now move up the slope of the RF waveform there and pick up. Okay, the path becomes shorter. The particles will arrive at the RF earlier and see the corresponding voltage due to this shift in time, and pick up the required energy to match. And so there's sort of self-synchronization, if you like, of the momentum with the B field. So we actually accelerate by changing the B field, and then the beam picks up the required energy from the RF system to stay in sync with the RF. Another important point is the power converters. Just very briefly, so these are critically important, very rigorous demands on these guys. The main dipole power converters is 10 volts delivering 12,000 amps with parts per million demands on the accuracy, and this is just tracking between three of the main circuits in the quads and bends in sector 3.8, in sector 7.8, and you can see this is fairly old, but you can see these guys are delivering the requisite current in step and to the actual individual requirements on these guys. So phenomenal performance of the power converters, and a very important component of operations for us. Okay, and that's just Okay, that's, yeah, okay, again, 18 milliamps, so 1.4 parts per million between sector 1, 2, and 2, 3, between two different sectors over the entire ramp. Collimators, okay, an interesting plot. So this is the jaw position in the ramps, and all these guys are moving in as we go up the ramp. And the result of that is the losses for beam 1 and beam 2. So each one of these lines is a bunch, and this is the percentage loss integrated over from time 0. And you can see going up the ramp nice and smooth, and when the collimators start to come in at the end of the ramp, the loss rate goes up. But okay, we're looking at 1.5% here, and 1% for beam 2 in this case. So very healthy. So we can actually do it on a good day. The squeeze we looked at yesterday, so I'll just flash this. So here, of course, we're reducing the beam size at the interaction point. The beams are still separated. We're going to go from 11, 10 meters in 1, 2, 5, and 8 down to 60 centimeters, 3 meters, 60 centimeters, 3 meters, with the collision tunes, with the orbit feedback on, and worry about things like tune, chromaticity, coupling, orbit, optic corrections, beam loss, instabilities. Okay, we had very tight collimator settings last year and made us very susceptible to small orbit movements during the squeeze. We also had some interesting instabilities. And okay, this is an example from July last year, and this is the tune being measured. So time 0 is down the bottom, evolving upwards, and somewhere towards the end of the squeeze, the beam's gone unstable, and sustained beam loss with both beams finally dumping on a collimator temperature interlock. So we were dumping so much beam on the collimators, they overheated and dumped the beam because they got too hot and bothered. So this was, okay, we can do it on a good day, we can do it okay, but not totally trouble-free last year. In practice, we're running from this, from the high beta to the low beta through a series of matched optics. So these are strengths in all the quadrupoles involved. I showed you the plot yesterday. We go from the IP, from the triplets, out into the arcs. And this practically is done by sending currents to the power converters, and initiated with the timing event. And here you can see the squeeze unfolding. So not a lot of rhyme or reason there, but this is up Q4, Q5, Q6, Q7, Q8, Q9, and you can see and this is changing the focusing properties in that particular interaction region to give us the required beta star. So that's the actual mechanics. And then finally, we get into stable beams, where we sit for as long as we can and watch the beam intensity drift down slowly, luminosity losses to the collimators, and the luminosity going down as well. So due to the individual beam losses, beam losses and some emittance blow up, but a healthy performance there. This could either we do periodic scans, so we're remarkably stable once we get into stable beams. The orbit feedback's off, and drifts are very, very slow. But occasionally we do we just check that the beams are still colliding head-on in the interaction point. So we actually do small scans to make sure. And so we separate the beams and then sweep them across each other in the vertical and horizontal plane. And again, that'll show up as a dip. The luminosity will drop as that scan's being done, and then climb back up. And here you can actually see a step up in luminosity following the scan, and not much change in this one here. If it's not that, it's because the experiments stopped sending data. There is, yes. So no, yes, very good. I didn't want to go into too many details, but that's another function that is downloaded from at the prepare ramp time to the RF, so the frequency change, there is a frequency swing. There's a voltage, the voltage changes, there's longitudinal blow up in the ramp. So there's a lot of things going on in the longitudinal plane, but okay, there's another one of these slides. It's called to see a Ralph. So this is we got some beam-based feedbacks out there. Just to know, I won't go into too much detail, but okay, here this is the orbit energy feedback. So Ralph is picking up data from all the BPMs through a feedback loop and hitting orbit correctors around the ring to keep the orbit where it should be. He's also got control of the RF frequency, and he can also do radial steering. So by changing the RF frequency, you can keep the beam centered in the beam pipe. And very, very quickly, 108 BPMs, coming in at 25 Hertz. So he's getting real-time feed from the BPMs at 25 Hertz, calculating a correction and sending that back down to the power converters, driving the orbit correctors. Okay, and then this is mandatory in the ramp and squeeze, and this provides us with a stability of around 50 microns RMS during the ramp and squeeze. So this really is, the aim here is, of course, to keep our small beam right in the center of the beam pipe, and very importantly, right in the center of the collimators. Tune feedback is also on. So we saw this yesterday, the tune diagram. This is what would happen if we didn't have the feedback on and we hadn't feed forward corrections. It'd go walkies and go crossing resonance lines, and we lose beam. And this is a sum of many fills. So here you have the vertical tune and the horizontal tune, beam 1, beam 2 during the ramp. And you can see the tune feedback doing a very good job for us there. Okay, the next important feedback system is the transverse damper. Again, this is bunch by bunch, turn by turn, some serious signal processing and correction going on here. So this is picking up data from 2 BPMs and sending corrections to fast electrostatic kickers to damp the motions of the bunches. So we use this all the way through the cycle. So this is an injection. The beam comes off with a kick, not perfectly injected on orbit. It will then oscillate around the orbit and end up blowing, getting bigger. And this is off and this is on, and you can see the transverse feedback locking onto the bunches and damping this motion down in a few turns. So very important. And this is the ADT as seen from the CCC, according to Danielle. Okay, pickups, signal processing, and the power to the kickers. Okay, that's how it's seen from. That's how he thinks we see it. This is how we really see it. On, off. Okay, that's it working. Cool. We got very high level of abstraction. But the transverse feedback is this is really cute stuff. I mean, this is used, okay, you saw for damping injection oscillations. We also use it for cleaning the gaps between for cleaning where we're going to inject, for cleaning the abort gap, because beam will drift in there. It's used throughout the cycle to damp potential instabilities. So a very important system. Okay, change the subject now. Operations 7 pillars of wisdom. Okay, given an impeccably debugged, optically good machine with an excellent magnet model, operations can then rely on. Okay, this stuff is done by the team of accelerator physicists, the magnet guys. During commissioning, we then look for availability, reproducibility, control, instrumentation, optimization, stability, and sometimes some understanding, and safety systems. So this brings me to machine protection. So last year we had 3.6 gigajoules of energy stored in the main dipoles, 144 megajoules stored in each beam. So 21 kilograms of TNT being threaded around a superconducting machine in in a superconducting environment, we've got to be very, 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 very careful. So we have a beam interlock system which is going to interact with the beam dump. Okay, a lot of care, as I said, taken here. Anything comes hot or bothered, it will trigger the beam interlock system to dump the beam. Okay, there's also a powering interlock system taking care of the safety of the superconducting magnets, which is going to interact with the beam interlock system. We're also going to distribute some safe key parameters which other systems need with absolute reliability. The BLM's thresholds change with energy, so they need to know what the energy is. So there's a system there for distributing these so-called safe LHC parameters with absolute reliability. So the beam interlock system, very quickly, is there's 4 dedicated fiber optic channels which run around the machine. Okay, this is inside is the beam, outside of these loops, and so they go out clockwise and anti-clockwise. And users are going to plug into this, and if any one of them decides they want to pull the permit, they hit the necessary card, and the beam is dumped. The signal goes off to the beam dump, and the beam is dumped within 3 or 4 turns. So this is right, get the beam out as fast as possible. So one turn around is 89 microseconds. So this is absolutely, completely critical. Which brings me to the beam dump, which of course is, if we ask the beam to be dumped, it has to dump the beam. So I'll just quick. We're going to go into the tunnel, so see this for real in a minute. But we've got fast kicker magnets, 14 of them, which are, so we've got beam 2 coming this way. This is going to kick the beams horizontally into 15 scepter magnets, which are going to then guide the beam up vertically off into the beam dump channel. We've got dilution kickers. Okay, there's a beam dump block, and to give you an idea of the scale. These guys are going to sweep the beam as it goes down the beam dump line to spread out the deposition of the energy on the face of the beam dump block. Okay, right. So this is there's a bit of fast mowing here.
Okay, we're in point 6, and these are the extraction kickers for beam 1, T2D. They're offering protection to the downstream sector.
$15 scepter. So we've got beam 1 and beam 2 there. They're sort of sitting in the middle. Beam 1 on the against the wall there.
Okay, the sector have guided extracted beam 1 up into the upper height of the 3. They're finishing the installation of a full complement of dilution kickers. Okay, I'm going to wander on a little bit further. So there you go, you see actually the beam pipe's actually getting quite big now.
So this is this.
Pipe.
Okay, carry on down sector 6, 7. You can see the arc bending away. You're arriving at the point where the beam dump pipe goes off down beam dump tunnel. We suspect that's going to be as far as we go. It's usually restrict the access of that tunnel. We're now looking down the beam dump tunnel. Okay. Display radiation area. If we were to channel down 700 metres, we come to the beam dump block.
Now all that lot has got to work with an incredible degree of reliability, and this is going to, I think it's still 4. I mean, this is allowed to fail on request once in, I don't know, over 10,000 years. And so you imagine the effort that goes into keeping a system that size in good operational state is quite remarkable. And I think it's quite worrying looking at it. Okay, we've got an abort gap of 3 microseconds. The beam dump kickers, the extraction kickers are going to come up to their full value during that 3 microseconds. And we've got a potential issue that if there's a misfire of the kickers, and so instead of hitting the abort gap, it hits the beam, it's going to sweep bunches across the aperture of the ring. So this is the extraction channel. So this is the beam pipe, the beam pipe that we saw. And downstream to mop up stuff are some big jaws, single-sided, which are going to pick up going to mop up as much of this swept beam as it can. Some will inevitably escape into the ring, but hopefully not enough to do any serious damage. So TCDQ is 6 meters long, and TCSG is 1 meter long. So this is a carbon fiber compound. So this is allowed to happen at least once a year. I think we've got 1 event so far. Right, which brings me to the collimator section. I think Belen was here, so this is swiping her slides. So I won't go into too much detail. 108 collimators, lots out in 0.7, 0.3, and then around either side of the experiments. And you see these are going to come in and mop up the beam. The idea is these mop up the beam before anything else does. There's a handsome young man standing in front of a collimator jaw. So this is about 1 meter long, and these are going to come in two-sided, so horizontal, vertical, or skew. And let's put those around. I do pedagogical collimation, courtesy of Ralph Assman, to explain the hierarchy. So these guys are going to be divided into primaries. The primaries are going to be closer, secondaries. We've got these dump protections, the DQ, which we just saw. And the idea is these are going to shield. Okay, we're going to besides shielding the machine, we're all going to also worry about the experiments and our precious superconducting triplets. So we go to normalized phase space. We divide by root beta, and the primary throws a shadow. And unfortunately, this asynchronous dump is going to throw a bigger shadow if we get one of these asynchronous dumps. So we have to make sure our tertiaries are properly out of this potential envelope. These are robust, so carbon-carbon is quite robust. Dump protection stuff is robust, but this stuff in here, the triplets certainly aren't robust, and the tertiary collimators aren't. So the idea is here the tertiaries are also very efficient, but so we spend a lot of time making sure that our tertiaries are nicely tucked behind the shadow of the rest of the system. And we call this arrangement the hierarchy. Okay, must be respected at all times. These guys are positioned with respect to the closed orbit. So the closed orbit clearly has to be in the right place at all times. So this is during the ramp and squeeze. So this motivates the orbit feedback being mandatory. And we have interlocks on the orbit position, so the beam in certain regions wanders off too far, bang, beam's dumped again. And okay, just again, a fixed display from the control room showing you the collimators on beam 1 in 0.7. So these are in millimeters. So our jaw, so you can see this. So these are kind of vertical, horizontal skew, a bit of a mixture here. You can see the idea here is we're defining a very small aperture and threading the beam through this hole. And if any particles wander out too far, they're going to get mopped up here rather than in our superconducting magnets. And okay, this is just a plot showing the orbit stability during the ramp, which just proves that the orbit feedback system is able to actually make sure that the beam stays in the right position as it goes through these guys. And just you've seen this before. So this is a loss map from Stefano, so deliberately provoking losses and checking that the collimator sections, the collimators are picking up the particles rather than the magnets. So out in the arcs, very small losses, very efficient cleaning from the collimation system, and a very impressive result. And this is routine collimation of 140 megajoule beams without a single quench from a stored beam. So that's our lines of defense there, which brings us to the end for today. Just want to mention control very quickly. So this is the SPS in the 90s. So you need 9 people back then to run a small accelerator. There's a young Delphine, a younger Lasser, and a Guy Crockford. Okay, by the time we got to the LEP era, we could do it with one man. It had to be Andy Butterworth, but okay. You can see this is the end of the LEP era. Of course, the LHC with improvements, things are a lot more relaxed now. And you've got one man running the whole kit and caboodle while Guilain picks his nose and film and stop pop stars come and visit us. Okay, thank you. Any further questions?
The block diagram of the RF control system was showing actually 2 almost independent systems. But I guess the 2 beam synchronization to each other happens already there.
You're right. We can actually separate the systems, and we do when we're doing proton ion, for example. But normally those frequencies are locked very tightly. Okay, lunch answer.
Mike, for the ADT, for the transverse damper, this means that you have a line which is crossing the ring of LHC, bringing the signal?
It's not. They're next to each other. I think it's a bit of poetic license, so it actually waits a full turn before it acts. So you actually have to do that transport around.
So it goes through the tandem?
No, they're sitting next to each other in point 4. So the BPMs are in point 4, the kickers are in point 4. So you have to, they have to kind of, take into account the fact the transport of the measurement all the way around. So they measure the phase very carefully during setup time, the phase difference between the kickers and the BPMs. So it's not actually stochastic going across the ring. Okay, thank you very much.